We can hear
Oh,
you.
good.
Perfect. So our next speaker is Viktor Jahnke. I hope I'm pronouncing that correctly. And he will be talking about holographic teleportation and conservation laws, diffusion on transversable wormholes. So take it away, Viktor.
Well, thank you very much for the introduction, Alberto. Let me first thank the organizers for the opportunity to talk about my recent work. So this work was done in collaboration with Byung-Jung An, Song-Gun Bak, and Kyung-Young Kim. Okay, so let's start. So recently, Gao, Jeffries, and Wall realized that wormholes in AdS can be made traversable by coupling the two asymptotic boundaries. And from the boundary perspective, the traversability of wormholes can be thought of as a teleportation protocol. Okay, this has interesting implications to study holographic systems in the laboratory. But let me first say that the effects of conservation laws on traversable wormholes have not been explored yet. So in this work, we try to fill this gap in the literature, and we study higher dimensional wormholes that are made traversable by coupling the two asymptotic boundaries with conserved current operators. So let me try to give you some motivation for this. So the traversability of wormholes is typically connected to their scrambling properties. And on the other hand, the scrambling properties of black holes change under the presence of conservation laws. For example, OTOCs, which typically behave exponentially for in the case of scalar operators, if the OTOCs involve conserved current operators, they display a power law behavior with time. This happens at late times. So this sort of suggests that conservation laws affect the traversability of wormholes. For example, the wormhole opening in principle can depend on the transport properties of the black hole horizon. And I think this might have consequences in many-body quantum teleportation protocols, which is like the field theory side of this traversable wormhole story. Okay, so I'll try to explain better these topics in the following. So yeah, so we are going to be working with asymptotically AdS two-sided black holes. So the Penrose, the corresponding Penrose diagram is shown here. So this geometry has two asymptotic boundaries in which the boundary theory lives. So we have a boundary theory that lives on the left, a copy that lives on the right asymptotic boundary, and the geometry on the left and on the right is connected by a wormhole. And we know from the AdS CFT that this geometry is dual to a thermofield double state, which you construct by entangling the two asymptotic boundaries. So this from the causal structure of this diagram, you can see that this wormhole is not traversable. And that the non-traversability of wormholes is connected to the so-called average no energy condition, which I will explain in the next slide. Okay, so the average no energy condition basically states that the stress energy tensor integrated along no geodesics is positive. Roughly speaking, this is basically telling you that the energy of your matter fields is positive. So let's say you have a signal that you want to send to the other side of the geometry. And you can see here on the left that the signal just hits the future singularity and never reaches the right exterior region. So maybe to make this signal to cross to the other side, you say, okay, I will introduce some matter fields on the left side, on the right side, and maybe after the interaction, my signal will be able to cross to the right side. And it turns out, like in this particular configuration, this matter field has a simple back reaction in the geometry, which is given by some shockwave like back reaction. And you can see that as the signal crosses the shockwave, the trajectory changes in a very simple way. It just gets a node shift. It gets a shift in one of the node directions. And this shift is proportional to this integral of HVV. Now, if you use Einstein's equation of motion, you can see that this integral of HVV is proportional to the integral of the stress energy tensor. And we know from the average no energy condition that this quantity is positive. So this delta U is basically positive, and only the matter fields only make the situation worse. So it becomes even more difficult to cross to the other side. So you can see from this picture that U needs delta U, which is negative. U goes like this. So you need delta U that is negative, which is basically telling you that you need something in the bulk that has negative energy in order for your signal to be able to cross to the right side of the geometry. Okay, so let me talk about Gauss-Jeffreys and Wall construction of a traversable wormhole. Gauss-Jeffreys and Wall construction, well, they work in the context of semi-classical approximation. So classically, so let me say that classically, you have the no energy condition, which basically says that the integrand here is positive. So classically, this condition is always satisfied, and you can never have under reasonable, in reasonable theories, you can never have a traversable wormhole classically. But the idea of Gauss-Jeffreys and Wall is to introduce quantum mechanical effects. So they work in the context of the semi-classical approximation, in which basically they treat, on the left-hand side, you have Einstein tensor, and they treat the gravity fields classically, but the matter fields, they treat it quantum mechanically. So basically, you write Einstein's equation, replacing the right-hand side with the expectation value of the stress energy tensor. And their idea is to introduce a coupling between the two boundaries. And it turns out that this coupling, it changed the boundary condition for the bulk fields here. And in the end of the day, the corresponding field excitation in the bulk has negative energy. So this negative energy makes it possible to cross to the other side of the black hole. So I'll try to explain a little bit more about this in the following, of how to reach this conclusion. But let me say a few things about the boundary perspective of this teleportation protocol. Oh yeah, first of all, like having negative energy in the bulk is somewhat similar to the Casimir effect. In the Casimir effect, you have negative energy between two conducting plates. And that's basically because you're imposing some boundary condition for your electric field in the region between the plates. And of course, like if you compute the energy in the region outside of the plates or inside the plates, in principle, at first you get like a result which is infinite, and only after regularization you get a finite result. So you get some infinite energy in the interior region, some infinite energy in the outside region, but like if you subtract one from the other, you get a finite result for the energy inside, which is slightly below the energy vacuum. So this is somewhat similar to what's happening here in Gauss-Jeffreys and Wall construction. Yeah, so let me talk a little bit about the boundary perspective on this. Yeah, from the boundary perspective, let's say you have like the two boundary theories are represented by these planes here. And let's say you perturb the right boundary. So you perturb the right boundary, and after some time, this perturbation thermalizes and completely disappears into the thermal bath. So after some time, you turn a coupling between the two theories, and you wait a little bit more, and this perturbation rematerializes or reappears on the other system. And this is kind of amazing because this perturbation was already scrambled among the other degrees of freedom of the system. So this, from the boundary perspective, this is kind of very amazing, and this actually provides a specific way to study. This provides a new type of teleportation, which is called many-body quantum teleportation. And there are some specific proposals for this type of teleportation. Here I'm mentioning a paper by Chester and collaborators. And it's somewhat similar to like a normal teleportation. In normal teleportation, we have Alice and Bob, and they share an entangled pair. And like Alice measures, Alice wants to teleport a qubit to Bob, and she performs a measurement in some particular basis. And then after some classical communication, Bob is able to obtain the qubit from Alice. So here it's somewhat analogous, but like instead of an EPR pair, you have a thermal field double state, which sort of plays the role of the EPR pair. And I think this type of proposals for studying many-body quantum teleportation, they're very interesting because if you could somehow implement this for a system that has a gravity dual, you could use this to gain insights into gauge gravity duality and hopefully quantum gravity. You can get some experimental insights to better understand gauge gravity duality and this kind of stuff. So yeah, so that's kind of like the main motivation for this work, is to think about like, I'm going to be talking about just the gravity picture for teleportation, but the motivation is like on the left side, because you have some gravity behavior, and maybe you want to implement this in the laboratory. And what is interesting about this many-body quantum teleportation is that in the case of holographic systems, this phenomenon it has very distinct features as compared to other systems. Like this type of teleportation, many-body quantum teleportation, can be implemented in chaotic systems in general, but only in systems that have a gravity dual. This has a very particular behavior. So this type of experiment can be used to identify a system that behaves holographically. And also maybe if you could come up with such a system in the laboratory, you could use it to study quantum gravity somewhat from the experimental, not to study, but like to simulate quantum gravity in some sense. Okay, so let me talk about our construction, like Gao, Jeffries, and Wall construction, or in other papers by other authors, people usually consider scalar operators. And the scalar operators, they are not subjected to any sort of conservation law. So you perturb the system and the system quickly thermalizes, or the perturbation gets scrambled with the other degrees of freedom of the system and disappears in the thermal bath. But if there are conservation laws, then the dynamics is more constrained, and maybe the system fails to scramble. So the question that we would like to address is what happens to this type of construction if you consider conservation laws. So yeah, just for comparison, I don't want to go into the details in this slide, but I should say if you consider a perturbation, you turn on the perturbation. If you consider like a delta function perturbation for this double trace interaction, you can see that at late times, the average no energy, or how much the wormhole opens, depends exponentially on the insertion time. T0 here is the time at which you introduce the perturbation. Yeah, so maybe I should give you a bit of more details about this. Basically, what I'm saying here is that I consider a perturbation like this. And this H here is the coupling that controls the strength of the perturbation. So in Gao, Jeffries, and Wall, they basically consider this H as a theta function. So the perturbation is introduced at some time T0 and remains in the system forever. But you can also consider like a delta function perturbation. In this case, you turn on the perturbation and then you turn off very, very quickly. And in this case, the result, this leads to simpler formulas for the wormhole opening. So the thing that we will be interested in this presentation is the average no energy, which is the integral of the stress energy tensor, which gives you this shift that I mentioned before. And this shift, I will refer to it as the wormhole opening. Okay, so just to try to give you some context and some time to observe the information. But like, yeah, so Gao, Jeffers, and Wall, they basically showed that this average no energy, they were able to come up with some analytic formula for the result. And the result basically depends on the scaling dimension of the operators you're using to open the wormhole. And this on this quantity V0, which is given by this, V0 is given here, and it's basically related to the time at which you insert the double trace deformation. So just for later comparison, I'm mentioning here in this slide that for the delta function perturbation, this average no energy has this exponential behavior. Okay, so a little bit of more details about our construction. Like, so we are basically replacing the scalar operators by some conserved current. And for simplicity, we just consider the time component of a conserved current. And as before, this conserved current introduces some negative no energy in the bulk. And this makes the wormhole traversable. And however, this conserved current operator is due to a gauge field in the bulk. And this gauge field has some diffusive behavior, which is controlled by a charge diffusion constant. And we would like to understand how the traversability properties of this traversable wormhole depends on the diffusive properties of this gauge field. Okay. So let me try to walk you through this calculation, but I don't want to go into the details, but like the basic idea here is that you start with your classical stress energy tensor in some generic background. And basically you want to compute the one loop expectation value of this stress energy tensor. And we do this by point splitting. So basically you can see that the only component of the stress energy tensor that will be interesting for us is the TVV component. And you can see that this TVV component at the classical level is given by a product of gradients of the gauge field. So to compute this by point splitting, basically you take the expectation value on both sides of this equation. And of course, like you have like here a 2-point function in which the fields are computed in principle at the same point. So this usually diverges. So what you do in the point splitting method, you just compute the two fields in different points. And by doing that, you can obtain the expectation value of the stress energy tensor from this 2-point function after some proper regularization. Yeah, so basically we need to compute this 2-point function. From this 2-point function, we compute the stress energy tensor. And from the stress energy tensor, we can compute the wormhole opening. And our hope here is that the deformation will introduce some modification in this 2-point function, which will make the wormhole traversable. So we do this calculation at first order in perturbation theory. So the perturbation here, it's basically given by the double trace deformation. And by doing this perturbative analysis, you find that like you have like the 0-order contribution for your 2-point function and the corresponding stress energy tensor. But at 0-order, the stress energy tensor, the average no energy is 0, because of course if you have no interaction between the two boundaries, it's the wormhole is not traversable. But if you compute the first quantum correction to this 2-point function, and there is a corresponding stress energy tensor contribution, and this can be non-zero by some choice of H. And in particular for our construction, the average no energy is violated if H is negative. Okay, so
Victor, you have 5 minutes left.
Sorry?
You have 5 minutes left.
Okay, good. Thank you. Yeah, so basically, if you do this calculation, you can see that this first contribution to the 2-point function is given in terms of some bulk boundary propagators, which in general are very hard to compute, but you can compute them in the hydrodynamic limit. Basically, if you solve the equations of motion for a gauge field propagating in the bulk, you find this typical diffusive behavior. You can solve the equations of motion as well for the propagators. And by computing the propagators, you can compute the stress energy tensor and finally compute the average energy condition. So, let me show you the result we obtain. So basically, for a delta function perturbation, we find this result, which has some exponential decrease, which is similar or reminiscent of the scalar field case. But we also observe some power law, which people have also observed it in the case of OTOCs. But what I think is interesting about this result is the fact that it's inversely proportional to the diffusion constant. So in principle, the lessons we can draw from this is that diffusion makes it harder to open the wormhole. On the other side, for some particular systems, the diffusion constant depends on some external parameters, and you can play a bit with these external parameters and make the diffusion constant smaller. And it seems like that this average no energy condition becomes arbitrarily large if you send the diffusion constant to 0. So on one hand, diffusion makes it harder to open the wormhole, but on the other hand, if the diffusion is very low, maybe you can violate average no energy condition by a large amount. And I think that the physical picture here is that this gauge field gives rise to a bulk field excitation, which is delocalized. And basically the signal you're sending from the left to the right side is shown in blue here. And it needs to interact with the negative energy to be able to cross to the other side of the wormhole. So, but since the interaction is weaker because the bulk field excitation is delocalized, this basically makes it harder to cross to the other side. You can also derive bounds on information transfer. And basically, like, I'm going to skip this previous slide, but in Gauss-Jeffreys and wall construction, Maldassen was able to show that the number of bits you send through the wormhole is bounded by this coupling constant h. In our construction, you can also derive this bound, but now you have an additional parameter to play with, which is the diffusion constant. Okay, so this is, and you can see, like, if the diffusion constant is really huge, this makes it more difficult to send information through the wormhole. Okay, so let me finish my presentation. So basically, we conclude that it's possible to generalize Gauss-Jeffreys wall construction to consider conserved current operators. And in this case, the wormhole opening depends on the charge diffusion constant, and it's inversely proportional to it. And I think this might have important implications in many body quantum teleportation protocols, which is the field theory side of this traversable wormhole story. And yeah, so future directions, I would like to say, like, I think it's interesting to the construction of traversable wormholes considering other fields. Sometimes these diffusion constants, they have lower bounds. And I think it might be interesting to investigate lower bounds on diffusion constant and how they relate to bounds in information transfer. And finally, I think it's interesting to study the effects of conservation laws in the context of many-body quantum teleportation. And so that's pretty much all I have to say. So thank you very much for your attention.
Thank you very much.